Welcome to the deep dive. Today we're jumping into, well, a really interesting corner of the OEIS, the Online Encyclopedia of Integer Sequences. We're looking at A000333. It's called the number of partitions into non-integral powers. Now, for you number theory students listening, this one connects things in a way you might not expect. Our mission today, to unpack this sequence and see what makes these non-integral powers so, well, special. Okay, so partitions into non-integral powers. That phrase itself is quite a handful. Could you maybe define for us what this sequence AN is actually counting? It sounds different from usual integer partitions.
It is, yes. It's quite distinct. Essentially, AN counts the number of solutions to a specific kind of inequality. We're looking for sets of positive integers, let's call them LES, and the rule is that the sum of their square roots, so some LES, has to be less than or equal to n.
Square roots, okay, that's the non-integral power.
Exactly. And there's another key constraint. The SI themselves must be positive integers, and they have to be in non-decreasing order, so 1 by 1 by 2 by 3, and so on.
So the order matters, and they're integers, but we're summing their square roots. That's quite a twist.
It is. It means we're not partitioning the integer n itself in the traditional sense. We're counting how many of these ordered sets of integers by 1 by 2 exist, where the sum of their square roots doesn't go over n.
Got it. That distinction is crucial. Introducing potentially irrational numbers, the square roots, into a counting problem seems like it would add complexity. Could you maybe walk us through an example, perhaps for a small n, like n3? The sequence says A3 is 15. How does that work?
Certainly. Let's take n3. So A3 15 means there are 15 such ordered sets by 1 by 2 satisfying the condition. Let's see. Some are simple. The set 1 works because square 1 works 1, which is less than or equal to 3. The set 4 also works since square root of 4, 2 still equals 3. And 9 works too as square root 9, it's 3, which is exactly 3.
Right. Single terms.
Then you combine them. The set 1, 1 works. So I'll start 1 plus 1 plus 1 plus 1 plus 6 plus 2, which is 8, 3. Or 1, 2. Square T1 plus square 2 is roughly 1 plus 1.41, so 2.41 still a 3.
I see. And the ordering by 1, get up by 2 means 1, 2 is the only way to list those two.
Precisely. We also have things like 1, 1, 1. That sum is 1 plus 1 equals 3, so that's allowed. But 1, 1, 1, 1 sums to 4, so that wouldn't count for n3. You keep listing all these possibilities, making sure the integers and ordered, and the sum of square roots doesn't exceed 3. You'll find there are exactly 15 ways.
That makes it much clearer. It's quite intricate. But here's where it gets really fascinating for me. This sequence apparently has a surprising history, connecting it to statistical mechanics. How did that happen?
Yes, that's a wonderful piece of the story. It turns out this exact structure wasn't initially dreamt up just for number theory fun. It first appeared, believe it or not, in a 1951 physics paper by B.K. Agarwala and F.C. Alok.
1951, wow.
Yes. Their paper was titled Statistical Mechanics and Partitions into Non-Integral Powers of Integers. They were exploring models for distributing energy quanta among particles. But, crucially, they considered scenarios where the allowed energy levels weren't nice, neat integers, but were proportional to the square roots of integers.
So like energy states square 1, square 2, square 2 thirds, etc.
Essentially, yes, or related to that structure. So the problem of partitioning a total energy n under these rules becomes exactly the combinatorial problem defined by A000333. It was later picked up and cataloged by Sloan in his handbook and encyclopedia, which really brought it into the mainstream of integer sequences, a great example of cross-pollination between fields.
Yeah, it's incredible. A number theory problem born from a specific physical model. And when you look at the sequence values, 1, 5, 15, 40, 98, it starts growing very fast. The entry mentions A34 is over 8 billion. That's explosive growth.
It is. That rapid growth is typical of many partition-related functions, but the non-integral nature here adds its own flavor. It strongly suggests a rich underlying combinatorial structure. While finding a simple generating function is complicated by the square roots, its asymptotic behavior, how fast it grows for large n, has been studied.
So the numbers aren't just abstract counts. They reflect this deep combinatorial complexity stemming from that square root rule.
Exactly. It underlines how many ways you can satisfy that inequality, even for relatively small n.
What a fascinating dive into A000333. We've unpacked its definition, summing square roots of ordered integers up to n. We saw how it works with the NE3 example and traced its really surprising origin back to statistical mechanics.
It really does make you think, doesn't it, about how these mathematical ideas pop up in unexpected places and connect different areas of science.
Absolutely. So for you listening, here's something to chew on. We saw A and N, uses square roots, partly because of that physics connection. What if we changed the power? What if we looked at partitions into cube roots, ISI13, or even something stranger, like side into the power of 1 ref phi, where the phi is the golden ratio? How would those sequences behave? What mathematical landscapes or even physical interpretations might emerge then? Something to ponder until our next deep dive.